Hello everyone, my name is İlhan and this is my presentation for phys212 project. The title of the project is an optical analogy of quantum tunneling. To begin, let's discuss the purpose of our project. Quantum tunneling is a non-intuitive phenomenon in quantum mechanics where particles are able to pass through potential barriers that they wouldn't be able to overcome according to the classical physics. Since particles exhibit wave-like properties in quantum theory, their wave functions can penetrate into and even emerge from the other side of a potential barrier, although with exponentially reduced amplitude. The goal of our project was to create a visual and measurable analogy of this effect using optical tools. Rather than using actual particles, which would require sophisticated detection methods, we used a laser beam as an optical equivalent of a quantum particle. The laser was directed through stacked transparent glass slides, and we analyzed how the light intensity changed as it passed through increasing numbers of these layers. Light, like quantum wave functions, also exhibits wave behavior and undergoes exponential attenuation when passing through absorbing or reflecting media. Therefore, the exponential reduction of light intensity in our experiment serves as an analogy for the exponential decrease in tunneling probability in quantum mechanics. In optics, the Lambert-Beer law tells us that the intensity of light decays exponentially with the thickness of the medium it passes through. Additionally, the presence of interfaces causes partial reflection, as described by Fresnel equations. The combined effects of attenuation and reflection shape the transmitted intensity in our optical setup. Here is our optical setup. In our experimental setup, we worked in a controlled dark environment. A red laser was aligned to pass through microscope slides stacked at the center. On each side, we placed screens to capture transmitted and reflected light patterns. A polarizer filter was added in front of the laser to minimize central saturation and better distribute intensity for accurate image analysis. We recorded the laser spot for different numbers of stacked slides starting with no slides, then adding 10, 20, 30 and 40 layers. The images were analyzed using MATLAB. We converted the photos to grayscale and measured both the total and central light intensities by integrating pixel values. These intensity values were normalized with respect to the initial laser output and recorded for each configuration. Transmission values were found to decrease significantly with each added layer, and although reflection values also varied, they did not follow a simple trend. The data revealed a clear exponential decay in transmission intensity, which supports our theoretical expectation. As more slides were stacked, the central light intensity dropped rapidly. This pattern follows an exponential model, confirming that optical attenuation behaves analogously to quantum tunneling. Furthermore, we analyzed the ratios of transmitted and reflected intensities to their sum. The transmitted refraction declined while the reflected or scattered portion increased with each layer, indicating that less light penetrated and more was either reflected or lost. We also observed the logarithmic behavior of transmission. When we plotted the logarithm of normalized transmission values against the number of slides, the data followed a linear trend, reinforcing the exponential model. A fitted line gave us a negative slope, representing the effective attenuation coefficient. However, the reflection data presented an unexpected result. While theory would suggest a steady increase or plateau, the reflected intensity unexpectedly decreased at 30 slides and increased again at 40. This irregularity did not match theoretical predictions. This brings us to the error analysis part. Several factors may have contributed to the deviation in reflection behavior. First, slight misalignments between stacked slides may have altered the light path. Small angular deviations or gaps between glass surfaces could lead to unexpected scattering or interference. Second, imperfections like surface dust or scratches may have distorted the beam. Although cleaning was performed, perfect optical surfaces were not guaranteed. Third, camera limitations and fixed settings may have introduced minor biases. ISO and shutter speed were kept constant to ensure fairness across measurements, but this may have reduced optical exposure for higher layer configurations. Lastly, limitations in the MATLAB region of interest selection might have led to loss of peripheral data, especially at higher intensities or irregular beam shapes. In conclusion, our experiment successfully modeled the principle of quantum tunneling using a simple optical analogy. The exponential decay in transmitted light intensity across successive glass layers mimicked the behavior of a quantum particle encountering a potential barrier. While transmission data agreed well with theory, some deviations in reflection behavior highlighted the limitations of real-world implementations. Nevertheless, this model provided a visually intuitive and experimental feasible way of understanding a deeply quantum phenomenon using classical optics. Thank you very much for your attention.